Hi everyone, welcome back to more on chapter 12, where it's just going to be this video is going to be a short video on all the quantum numbers and what you use the quantum numbers for. So for this class, there are four main quantum numbers that are used in this class, and the four of them are: the first one is the principal quantum number. And what this is it's something that we've already used a lot. It's the n, so the row of the periodic table. That's the easiest way to remember this. And for this class, it's usually going to be either 1, 2, 3, or 4. So as you go down the periodic table, the number increases. So the first row is 1, then if you go down the second row, and 2, and then the third row is 3. And the second quantum number in this class is the angular momentum and then quantum number. And what this is it's written with an L equal to, and what this is the shape of the orbital. So in this class, we're going to be focusing on, there are going to be, I think, about 4 main orbitals. There are probably more in real life chem, but for this class, we're only going to be using, the S orbital, then the P orbital, then the D orbital, and then the F. We're barely going to touch on the F, but I think you still have to remember it. And for the angular momentum quantum number, the L is assigned, each of these are assigned a number. So S is assigned the number 0, then P the number 1, then D the number 2, and then F the number 3. And these are mostly the L's that we're going to be using in this class, and you just have to remember these ones. And then the third quantum number that is used in this class is the magnetic quantum number, which this determines the shape of the orbitals. So for example, first of all, the letter for this is ML. I mean, the notation what you use to show the magnetic quantum number is ML. You remember, because magnetic starts with an M. And what this means is just the shape of these orbitals. So later on in the class, you realize that there's only one possible S orbital, which is just a circle. And then for the P orbitals, there are 3 possible configurations for the P orbital, which is, I think, the PZ, the PX, and then the PY. And they look something like this, like either next to each other, also next to each other. So positive, negative, then positive, negative, and then on top of each other, positive, negative for the Z. And for this one, the ML will be 0. Then for this one, it should be -1, 0, and then 1. So it goes from -1, 0, 1, and the other one -2, 0, -2, -1, 0, 1, 2. I'll show it soon in a moment. But for this one, for the P orbital, there are 3 MLs, and then I'll draw the D orbitals. So for the D ones, actually, it's going to take a while to draw, so I'm just going to tell you that they are 5 D orbitals. You can look them up to show how it looks like, because later on I think you might need to know how to draw one of these. And then for the magnetic quantum number of the D orbitals, we're going to be -2, -1, 0, 1, and 2. And then they're assigned to all the different shapes. And if you count these up, 1, 2, 3, 4, 5, you realize that there are 5 possible configurations of D orbitals, and that's what the magnetic quantum number means. And finally, the easiest one is just the spin, which is known as the MS, and it's either positive or -1/2. And what it determines is just the spin of the electron in the electron configuration. So like if you're putting it in, it's at this level, this is a positive spin, this is a negative spin. So that's just what the MN is. And these are all the quantum numbers that you can use to figure out a problem. And before I end the video, I'm going to give one example of how you can use these quantum numbers. So let's say they give you, in an exam, you're given something like n is equal to 1, L is equal to 0, and ML is equal to 0 as well, because it has to be 0. It can't be, the ML has to be you can't have an ML more than the L. But besides the point, if you're given these three numbers and then they ask how many electrons can this form, then you realize that you can solve this by looking at the n equals to 1, which means it has to be in the first row of the periodic table. And if you remember the electron configuration, the first row of the periodic table is always S, and then you confirm it with the L equals to 0. If you remember up here, when L equals to 0, it's the S orbital, and then ML is equal to 0. ML also has to be 0, because that's only one way for the S orbital to look, which is just the sphere. And you know this can only describe one electron. Or actually, since the MS isn't given, it can describe two orbitals instead. So the reason, if the only way it would be 1 is if there's an MS as well for the spin, and they tell you it's equal to positive 1/2, which means there's only 1. Another example of a way that this problem can be asked is, so they give you n is equal to 3, and then they can ask you what are the possible L values that you can get if you're given an n equal to 3. And how you do this is that you look at you remember that this means the row in the periodic table. So that means they're talking about the third row in the periodic table. If you remember, the first one's the S, then the second one's SP, then the third one can be SD. So there are 3 different configurations that n equal to 3 can have, which is either 0, 1, or 2, which is for S, P, or D, like I said up here. And if you did not want to reason this by looking at the periodic table, there's also a formula which is given where L has to be, the max L can be is n minus 1. So if n is 3, the max L can be is 2. If n is 2, the max L can be is 3. And that's how the L's, the MLs, and the N's all relate to each other.